Okay, so now let's focus in on the ampulla of a semicircular canal. So this is a bulbous expansion at the base of the semicircular canal. So this is where we find our sensory epithelium, which is called the crista. And overlying that crista is a gelatinous mass through which protrude the stereocilia of the hair cells. So this gelatinous mass here is called a cupula. And so we see the bundles of hair cells that are projecting into this cupula. Now again, there's no axis of symmetry that bisects the sensory epithelium as we saw in our otoliths. So there's simply one axis for depolarization that's present in a crista of a semicircular canal. Now this cupula creates a barrier to the flow of endolymph. And so what this means is that if we accelerate our head around an axis of rotation, it's something analogous to, let's say, rotating a cup of water. So the glass would be the membrane and the fixed components, and this cupula is indeed fixed here at its base along the crista as well as on the more distal part of the ampulla. So if we were to turn that glass of water, the glass turns, right? But the water has some lag because of the force of inertia. The same thing is going to happen here in the semicircular canal. As we turn our head, the force of inertia is going to cause a deflection of this cupula. So let's have a look at that. So here's the semicircular canal at rest, and then if we were to rotate it, so we are actually accelerating our sensory epithelium with a turning of the head. The lag or the inertial force causes endolymph to essentially flow in the opposite direction. Really, it's the fixed structures that are moving. The endolymph is staying more or less in the same place. That causes displacement of this cupula. And as you can see, this displacement is going to deflect the hair cells in this crista towards the longest stereocilium. That's going to lead to depolarization of all of the hair cells together in this one crista. Now, we're turning our heads to activate this particular ampulla of a semicircular canal. It has a functional pair on the opposite side of the head. The turning of the head in one direction is going to activate the crista on the side of the turn, and it will deactivate or hyperpolarize the hair cells on the opposite side of the head in the corresponding member of the pair. So let's see what this looks like from a physiological perspective. So now we're recording the discharge rate of an axon that receives a synaptic input from a hair cell in the crista of a semicircular canal. And we see that as we accelerate, that is, as we begin to turn our head, we see that there is now a transient response where there's a temporary increase over the course of a couple of seconds in the firing rate of this eighth cranial nerve afferent. But as we attain constant velocity, so you can imagine if you start to turn around in circles, I'm not going to be able to do this very long because I'm going to get dizzy real quick. But in the first few seconds of rotation, my left horizontal canal began to increase its firing rate. But as I was maintaining that rotation, essentially the movement of the endolymph caught up with the movement of the fixed structures, and so the deflection of the cupula now relaxed back down to its neutral position. And so the velocity of rotation was maintained, but the deflection of the hair cells relaxed after several seconds of rotation. So that is why this response in the hair cells and in the eighth nerve axons that innervate the semicircular canals is phasic. Okay? It's only transitory. Now, as we decelerate, we essentially are producing the opposite biomechanical effect. That is, we are reducing the rate of rotation, and that's causing the endolymph to flow against the decelerating crista or the decelerating cupula. And so that's going to now deflect the hair cells in the opposite direction. And that will produce hyperpolarization and a reduction in the release of transmitter on the eighth nerve afferent, and therefore a reduction in firing rate. And it will again take a few seconds to equilibrate the flow of endolymph and the flow of the fixed structures. So this is why the semicircular canals only operate with a phasic response rather than the sustained response that we saw in the otolithic membrane. I would encourage you to think through this again on your own. If you don't quite understand why would the otoliths give rise to a sustained response where the semicircular canals a phasic response, you might want to go back and think through this again to make sure that makes sense to you. It basically is explained by the biomechanics of sensory transduction. And lastly, I want to talk about the function of these pairs of organs on either side of the head. I alluded to this just a moment ago. But this is very important for understanding central processing in the vestibular system, and this is what we'll come to in the next tutorial. I want you to appreciate the fact that our otolith organs come in pairs. There are two utricles in either side of the head. There are two saccules in either side of the head. They tend to work together because they're arranged in the same plane. The semicircular canals, however, are a little bit more complicated because they're actually arranged orthogonally to one another within the same side of the head. So that means the functional pairs need to be thought of as those canals that operate in the same plane. Okay? So for the horizontal canals, it's pretty straightforward. Both horizontal canals operate in the same plane. But when it comes to the superior and the inferior canals, then we need to recognize that the superior canal in one side of the head is actually operating in the plane of the inferior canal in the opposite side of the head. And then vice versa. My right superior canal will be a functional pair with my left inferior canal. So this means that in order to activate these functional pairs, I would really need to rotate my head along the axis or within this plane, orthogonal to the axis of rotation defined by this orientation. So this forward tilt to the right would activate my right superior canal and deactivate my left inferior canal. And tilt back would do the opposite. It would activate the left inferior canal, deactivate the right superior, and so forth. Okay? So if I rotated down and to the left, I'm activating my left superior canal. Rotate my head back and to the right, I'm activating my right inferior canal. Now you may be wondering just about the head nod kind of motion. Well, we're going to activate both superior canals to some degree, not as perfectly as if we turned directly in their axis of rotation, but a forward tilt is going to produce phasic activation in both superior canals, and a backward tilt is going to produce phasic activation in both inferior canals. Now, the simplest of all to understand would be simply the shaking of the head left and right along the z-axis of rotation. Okay? So what would happen there is that as we turn our head towards one side, let's just say the head turns to the right, we would activate the right horizontal canal. So here's the ampulla of the right horizontal canal. And because of the inertia effect, the endolymph is essentially forced against the crista along its axis of depolarization, so we have a nice increase in the firing rate of the eighth cranial nerve on the right side of the head. That very same rightward head turn causes the endolymph to actually move in the opposite direction that would be consistent with depolarization for the left semicircular canal. Consequently, if the left semicircular canal is firing away, when we make that head turn, now it's going to decrease its firing rate. And then after a few seconds, if we keep rotating around, then we would expect it to recover back to its neutral position. So the key principle that I want you to take away from this slide is that we activate the semicircular canal on the side of the turn. So if we turn to the left, we're activating the left semicircular canal, the horizontal canal. If we turn to the right, we're activating the right horizontal canal, and so forth. Forward turn activates the superior canals. Backward turn activates the inferior canals. So what I really want you to understand is that when we get to the brainstem and talk about central processing, the brainstem is comparing the activity that's coming from both vestibular nerves. And if we turned our head to the left, we can imagine that in the horizontal canal system, leftward head turn would elevate activity in the left vestibular system and decrease activity in the right vestibular system. Whereas if we turned our head to the right, we'd have the opposite effect. Okay, so what the brainstem's really doing is comparing the afferent activity that's coming from these two eighth cranial nerves. Now imagine what would happen if you had a lesion or some kind of injury to the hair cells or to the eighth cranial nerve. You may find that the activity on the lesion side begins to drift downward. We call this unilateral vestibular hypofunction. If I had hypofunction on the right side, what's that going to make me feel like? Well, it's going to make me feel like I'm spinning to the left. And vice versa. If I had injury or damage to my left vestibular labyrinth or left eighth nerve, there will be hypofunction on the left, and it's going to make me feel like my head is spinning to the right. Well, that's a very unpleasant sensation, as you might imagine. Maybe some of you have experienced it for yourself. It illustrates the power of this vestibular system. And it's important that you understand these peripheral biomechanics and the means for sensory transduction. And this will allow us to now understand and discuss how the central processing stations operate and what are the consequences for the integration of these vestibular signals. So when I see you next time, we'll talk about central mechanisms of vestibular processing.